All right, so you have memorized the reactions for this chapter in the reaction list, and you're trying to apply them to these different alkenes for these synthesis problems. So you would look at a reaction like this, you would see that there is a pi bond, so you know you can do addition. What are you adding? You'd look at the other elements in the recipe here, and you would recognize hydrogen gas and either platinum, palladium, or nickel. You don't need all three, like are listed here. You really only need one of those. And if you have hydrogen, H2 gas, and one of those catalyst metals, then you would recognize this reaction as hydrogenation. So you're going to be adding hydrogen across the double bond. So you're saying, okay, hydrogenation, what am I adding? Where am I adding it? How am I adding it? In hydrogenation, you're adding hydrogens. So 2 hydrogens. Where are you adding them? Since they're the same group, it doesn't matter where you put one and where you put the other. They're identical. So it's a hydrogen on both positions. So that kind of doesn't matter. We don't have Markovnikov or anti-Markovnikov. Although one useful thing to note is that you don't have rearrangement. So you don't really have to worry about a carbocation rearranging in this problem. You'll always be attaching the 2 hydrogens to the 2 carbons in the double bond. And then how are they attaching? If you look at the notes for this reaction, you'll see that they're attaching syn. That means both hydrogens need to be facing the same direction. So either they'll both be coming towards you, or they'll both be going away from you. And you would really only have to indicate that if you had a chiral center. And that's kind of the other thing you have to watch out for. If you do have a chiral center, just keep in mind you'll have a racemic mixture of the 2 enantiomers. And that's just because you have a flat starting material. So there's a 50-50 chance that one side of the alkene, the double bond, will react, and a 50% chance that the other side will react. And of course, if you don't have a chiral center, you don't have to worry about that. It's no big deal, not applicable in the /A. So knowing those things, we can take this particular molecule, and knowing that we do not have rearrangement, we know that the 2 things we're adding are going to add onto the carbons in the double bond. Those 2 things are the same, so it doesn't matter where they go. So you can add a hydrogen on one end, a hydrogen on the other end. As you stick those hydrogens there, you use up that pi bond, so the pi bond should not stay there. And we don't form any chiral centers here, but if we did, we would want to make sure that the hydrogens are adding syn. Now, they're, because of no chiral centers, we don't have to indicate that, and so really, you could, if you drew this as the product, I would be more than happy with that. But also, because this is a skeletal structure, you would kind of want to get used to seeing it without the hydrogens drawn in explicitly, so that this would really be your product. And you'll notice that that allows you to draw the products for these really quickly for hydrogenation. Very often, with hydrogenation, all you have to do is sort of erase the double bond in a skeletal structure, and you'll get the product. And it's not just that you're erasing the double bond, you're also adding hydrogens, right? In this example, there are only 2 hydrogens here. In this on the left, there are 3. And likewise, there's only 1 hydrogen here, but on the left there's 2. So you've added hydrogens across that bond. But you don't have to draw them in because they're implied on the skeletal structure. So oftentimes you can quickly predict the product of these hydrogenation reactions really just by erasing that pi bond. And so that would be the product for that hydrogenation reaction. So let's take the same sort of thinking and try to apply it to another molecule. You see the alkene, the pi bond, and so you think, okay, I can do an addition reaction. What am I adding? You look at the reagents, and you would want to see hydrogen gas, H2, with either platinum, palladium, or nickel. You don't have to have all 3, so just 1. And when you see those 2 things, you'll say, okay, I'm doing hydrogenation, and that means I'm adding 2 hydrogens without rearrangement, and they would add syn. So you can take this molecule here, and really, all you have to do in this case is erase the double bond, the pi bond. And by doing that, you've really added 2 hydrogens across the bond, but they're implied. And you don't have to worry about rearrangement. They'll always add to the 2 places. The hydrogens will always add to the 2 places, the 2 carbons that were in the double bond. And in this case, we still don't have a chiral center. So we don't have to indicate that both of the hydrogens added on the same side. But if you did, you would just want to make sure you drew both hydrogens adding on the same side, and then anything else being pushed away. If you had a chiral center, and then you would draw the enantiomer, where all of the three-dimensional bonds switch. The solid wedges turn to dashed wedges, and the dashed wedges turn to solid wedges. But in this example, all you have to do is erase that pi bond, and by implication, you've added two hydrogens. So this hopefully helps you a little bit with hydrogenation reactions on alkenes when all of the reagents are given to you in these one-step syntheses.